have our second paper ready to go. So this paper was also nominated for the Best Reproducibility Advancement Award. So we have Thorsten Hoefler presenting the paper, Hamming Mesh, a Network Topology for Large-Scale Deep Learning. And we're ready to go.
Okay, thank you very much, everybody. My name is Thorsten, and I'm presenting this paper today. If I'm a little bit out of breath, that is related to the fact that I just ran over from the Turing reception, sorry. And I probably have to run back to meet Jack again. So this paper was actually a collaboration between Microsoft and ETH Zurich, my home university, and I did it. I did much of the work on this paper while I was on sabbatical in 2019 in Microsoft. But the idea at the time, and now the same today, is really that deep learning is a very large-scale computing problem. Actually, it's quite fascinating to see that many industries these days talk about supercomputers. And we have heard Jack's qualification of supercomputers, top 500 machines, extremely large machines. We build specialized machines for AI these days that are extremely large. Facebook, Tesla, other industries, and Microsoft invest hundreds of millions of dollars into these supercomputers. It's even so far that there are comics about the CTO of Microsoft standing there next to an AI supercomputer. So we are in the right field to drive the future of artificial intelligence here. But what is really artificial intelligence in some sense? So how does it work in a nutshell? I'm giving you an overview of about 30 seconds of how it works. So let's say you want to learn all of the human knowledge. What do? Well, you read the internet. Well, how do you train a model? Well, you take a sentence on the internet like this one. You remove a word on that sentence, you run it through a deep neural network to predict the missing word, then of course that network will give you some output for the word, some probability distribution, but then you know which word you removed. What you do then is you backpropagate the correct information in some kind of correction form through that network in an iterative way over and over again, such that the network at the end will learn a statistical distribution of natural language, which includes all the knowledge that is represented by the natural language. And you can now argue that this is all of humans' knowledge in that model, right? So this is where it goes. People have done this. You could train on the whole internet, essentially. Everything we are saying. What I'm saying right now is most likely going through some artificial intelligence network at some point that learns the way I'm just describing it here. Also, these networks are of incredible size. So in full precision, they could have 700 gigabytes just for a single model. This is GPT-3. These are models that are existing today that have been trained with millions of dollars. And of course, it takes weeks to train these models. So that's just the motivation for why I'm here. But what I actually want to talk about is the bandwidth, the properties, the computational properties of these models. And these are extremely demanding. So bandwidth is the new oil in AI supercomputing. Memory bandwidth is relatively easy. I don't want to offend anybody, but relatively easy to get. So we just buy HBM3. So let me check this off here. But network bandwidth is something that is extremely complex to get at reasonable cost. And this is what I want to focus on today. If you look at HPC networks, the exascale supercomputers deployed today, what Jack talked about in his keynote, for example, a Slingshot system, which is number one on the top 500 list, it has 200 gigabit per second bandwidth per GPU. With InfiniBand, you get 400 gigabit bandwidth, and now you have to argue about the ratio of GPUs. But if you look at AI systems, last year's TPU v2, and that was not developed last year. It was published last year, so it's actually quite old, has 1 terabit, 5 times more bandwidth. AWS Trainium that you can rent today, 1.6 terabit per second. DGX2, a machine learning box from NVIDIA, 4.8 terabit per second if you include NVLinks. And then at the top of the list is Tesla's Dojo, which was announced 22 with 128 terabit per second. They scaled it down since then, so it's not coming into practice. But this is more than twice as much as a network switch that is designed for pushing packets. So AI accelerators have more bandwidth than a network switch. So that is quite interesting. And then, of course, it looks from a computational perspective, it looks even more demanding. So these networks need more and more and more bandwidth, these problems. So we see a discrepancy between the exascale systems today and modern AI systems of up to 640x speed. So somehow AI is entangled in a mess of cables that we need to deal with. And if you build these systems, you will actually realize with standard HPC topologies like a fat tree with 16,000 endpoints, that's going to be $680 million. So that is way too much. So we cannot afford conventional HPC technologies in the AI space. So what do we do? Well, how does it look like? Well, first of all, let me explain a little bit how parallelism works in AI. What we really do is we have lots of text. So here these mini batches that I'm showing you is again the text that I showed before. And what we could do is we could just replicate the model across multiple GPUs, here in this case 3 different GPUs or 3 different accelerators in general, in the green, the blue, and the red one. And we can draw from this text and run different examples through each of those and then synchronize those. But the problem is the model cannot be replicated if it's 700 gigabyte of size. There's no GPU that takes 700 gigabyte. So we need more distribution of the model itself. So one of these distributions, we could use pipeline parallelism, in where we put every single layer of the model on a different accelerator. Here again, green, blue, and brownish, I would say. So this is one form of distributing the model itself, obviously. There's another form, a third dimension of distributing the model, if you actually want to make these operators faster. So here in this case, I'm splitting each of the layers, each of the matrix multiplications in 3 components, again, blue, red, and blue, green, and brownish. So these are 3 different ways, and I call this 3D hybrid parallelism, to cut a network into pieces, to cut the computation into pieces. So usually when we run these very large models, we are combining all 3 of these ways. But let me now look at the communication properties of this, because we were talking about networks, interconnection networks. We got to talk about communication. What is the communication behind data parallelism? Well, it's synchronizing the models. It's an all reduce. It's a sum. We're just summing up the gradients before we apply them to find one single gradient to apply. And this can be implemented with a ring communication. So the second, the pipeline parallelism communication, is relatively obvious. It just goes from layer n to layer n plus 1, or layer I to layer I plus 1, and back, because in the backwards pass it goes backwards. The operator parallelism is another all reduce in the common case, because it's a matrix multiplication. If you split matrix multiplication, you're most often doing this along the reduction dimension, and then you split it, or then you perform an all reduce operation again. So we have basically 3 operations that are doing nearest neighbor along 3 different directions. So now, if you look at this together, these 3 operations, well, we get one large 3D torus. Great. And at the end, this is our communication pattern that the application is doing. We know this from stencil applications, actually, in our field, quite similar, but much more bandwidth here. So now the question is, how do I design a network that is optimized for that particular workload at reasonable cost? As I mentioned, we don't want to spend $680 million building a 16,000 node system, because nobody's going to put up that money. What we did is we looked at a specific design that I want to discuss, which is on a 2D layer, on a 2D surface, so to say, because everything is in 2D. A chip is on 2D, a board is on 2D. If we can go 3D, it's an easy extension of the model that I'm showing here, but I'm showing 2D. So what do we do? Well, we have this accelerator package. We add 4 network links, 4 directional network links in 4 different directions, north, east, south, and west. Sounds very familiar to you if you know stencil computations. We add a little packet switch for those. So it's a 4x4 switch, and then we add multiple of those that I would call planes. So now, if these are 400G links, this accelerator is going to have 1600G, if this is 100G links, we are going to have 1600G connectivity to the outside world. Then we arranged each of these accelerators on a 2x2 board, let's say, and we have very cheap, here dotted on-board connections. Then we take those boards and arrange them into a larger 2D grid, as you can see here. So, in this 2D grid, we now do not connect only with nearest neighbors, because then it would just be a torus, and a torus is relatively inflexible. So what we do here is we build a 2-dimensional Hamming graph, or you can call it a 2-dimensional hyper-X if you want, or diameter 2 hyper-X. And each of these planes is now fully connected in both the X direction, but also fully connected in the Y direction. So you can now build different designs. You can now build larger boards, for example, a 4x4 board, which has more onboard connectivity, which is relatively cheaper, because these PCB traces that are here dotted are literally free. But then at the end, it's the same. Each of those accelerators has 4 directions per plane. It has 4 planes per accelerator in this design. And it has A times B many accelerators on this board, or per board in general. And again, these interconnects that are on board are relatively cheap. They're actually free if you look at the packaging cost. So this gives us an interesting trade-off between the global topology, the fat tree topology that gives you all flexibility you can dream of, and the torus topology, which is the cheapest, but is extremely limited, as we all know. So now the Hamming mesh is somewhere in between. So you can now play with these local torus networks and connect them with a global 2-dimensional connectivity pattern to trade off reduction bandwidth, global bandwidth, placement flexibility, and injection bandwidth. And somewhere every Hamming mesh design lies between those 2 extremes, like a local torus and a global fat tree. Okay, so let me talk a little bit about modeling and theoretical cost analysis of this topology. So let's assume we have an A by A board arranged in an X by X 2D Hamming mesh. So the A is going to play the major role. So we had A equals 2 and A equals 4 on the previous slide. If you look at the relative bisection bandwidth of this network, it's always going to be 1 divided by 2A. So for a 2 by 2 Hemming mesh, it's 25%. For a 4 by 4, it's 12.5%. If you look at the diameter, it's respectively 4 or 8. But what is really interesting is the cost model. So the cost model is the core of this whole design, because it's all about money at the end. If we can afford, if we're willing to spend infinite money, we just build a fat tree, we're happy. Like, it's less complication. But we cannot. So what we did is we actually looked at the exact costs at the time for switches, cable, and various forms of cables, AOC cables and DAC cables. And one of the interesting insights is, don't look at the details of the numbers, I'm just putting them there for reference, is that actually the cables that come out of a switch are more expensive than the switch itself today. That is interesting. And these cable costs are highly varying. They depend on all kinds of different factors. So for this, we actually give you a spreadsheet in the reproducibility package that is somewhat of a topology builder. It's the first of its kind. It's really, really, really cool. Industry got really excited about it. We have the spreadsheet that can explain or get you the cost for all the topologies that I'm going to mention, including all the Hemming mesh configurations that you can dream of to reproduce our results, but also bring your own results, because these numbers are not valid anymore. These numbers were valid 6 months ago when we submitted the paper, or maybe even 9 months ago. Today, they're different. So when you do a design, you take our spreadsheet and you build your system with that spreadsheet. Right? That's the idea. So we have an example small topology, of course with the old numbers, an example large topology with also these old numbers, always in the configuration with 2 by 2 boards and 4 by 4 boards. So let me start with a large cluster, because nobody wants to talk about small clusters these days. It's a supercomputer. It's going to go on the top 500 list, of course. We have a large variety of topologies. We have non-blocking fat trees, tapered fat trees, dragonflies, HyperX topologies, Hemming mesh, and 2D torus topologies. We can look at the cost. I don't have enough time to go through the cost, even though I speak very fast, I know. So we have a cost ranging from $680 million for the fat tree, right? This is the example I had at the very beginning, extremely expensive, down to 40 million, a factor of 15 less in the torus case, and the Hemming mesh 4x4 is just slightly more expensive. If you now look at the global injection bandwidth, that's basically all-to-all bandwidth. This is when everybody communicates to everybody. We see that the non-blocking fat tree gets you basically all bandwidth. This is a packet-level simulation using the SST toolchain that we spend about 0.6 million core hours on to just run all of these simulations. We can see that the torus is extremely bad. It's just abysmally bad. It's at 1% bisection bandwidth, essentially. That's close to 0. And we see that Hemming mesh performs as expected, about 25% and 10.5%, which should be 12, but of course there are artifacts in the routing and whatnot, so it's not always perfect. And if we now look at the cost per bandwidth, per global bandwidth, we see that relative to the fat tree, so fat tree gets 1x here. You can see that Dragonfly is a little bit better than fat tree. We can see that Hemming mesh, HyperX is a little bit better, but the 4x4 Hemming mesh is even better in cost per bandwidth, which is a very interesting measure. It has absolutely less bandwidth because it's only 1/10, but it's 15 times cheaper, right? So you get more bang for your buck. Then if you look at the all-reduced bandwidth, which is another interesting aspect, it's literally just how fast can I do an all-reduction on these topologies. You see nearly all topologies have close to 100%, because all-reduced does not require a high bisection. All-reduced is a very flexible algorithm that I can map into rings. If you look at the cost per injection bandwidth of the all-reduce, you see that it's 15 times better for the Hemming mesh topology than it is for the non-blocking fat tree. The other ones are also competitive. We see the 2D torus is even slightly better, but remember, the 2D torus has basically 0 all-to-all bandwidth. So that is a big problem. This is why we like this topology. Now the question is, how can we map jobs to that topology? Well, if mapping 1D or 2D jobs should be pretty obvious, because it's a 2D structure. Mapping a 2-dimensional job, you just map it on the thing like you would imagine. A third dimension is also relatively easy to map, but I have a visualization here. Let's see, we have a job layout that has 4 by 4 by 2 parallelism. So let's say it has data parallelism 4, so 4 GPUs in the data dimension, pipeline parallelism of 2, and operator parallelism of, pipeline parallelism of 4 and operator parallelism of 2. You typically don't want to cut your operators very wide because they communicate extremely heavily. That's the bad dimension. That's usually the small one. And if you map this to a physical Hemming mesh, you would basically just flatten it into a 2D representation. So that's not hard, I would say. Fault tolerance is an interesting topic because now in a torus, fault tolerance is a disaster. You somehow need to route around elements of the torus, a huge problem. But in Hamming mesh, it's actually quite nice. If we just agree that if a node fails, we fail the whole board. Like if you have a 4x4 node, one node fails, we just scratch the board of our job. We can still run single node jobs on that board if we want, but it's not part of bigger jobs. So let's say we fail these 3 boards here, and now we can still map jobs. So who sees how to map the 2x4 job onto this topology at full bandwidth? It's relatively easy to see, this one, right? Because I can commute every row and every column. Now, I give you the task to look at the 3x3 job. That's a little bit harder. But you can still map the 3x3 job at full bandwidth on this topology. You just have to find the permutations of rows and columns. It's a little bit like puzzling, where you have to map this job. And as I mentioned, it's a little bit like puzzling to get this flexibility. So we designed an allocation scheme that, of course, does it automatically, because we don't want humans to puzzle whenever there's a job coming in to figure out where it goes. So here again, we have a script that implements all the allocation schemes that we talked about. I don't have enough time to describe them. They're simple, greedy schemes. You can find them in the paper. But I want to highlight this script, which comes with a visualization where you can actually implement your own scheme and reproduce our schemes to do the process mapping yourself. So if you look at this here, for example, you see there's a 1x1 so it's an 8x8 Hamming mesh allocation. And so the one in the top left, the 9 ones, means that's a 3x3 set of processes. Then the scratched out red ones are essentially these that are broken. And then the second job is also a 3x3 job. So you can see that you can really run your own allocation on the thing. You will get a visualized output, and you can play with that as much as you want. So what did we do? And again, you find all of this in the reproducibility package. What did we do? Well, we ran a machine learning as a service workload from the Alibaba data set that was shared with us on this allocation, on this network. So we literally just sampled from that CDF, and we just allocated it to the machine. And here we get this relatively complex plot. But what I just want to highlight, if we play all the tricks that I didn't really talk about, but they're relatively simple in the paper, we achieve nearly always 100% utilization of the topology. So just imagine it being a relatively simple, greedy scheme. But what is more fascinating to me, if we introduce random failures to the topology, even if I have 40 nodes failing out of 64 total nodes, I still get about 90% allocation efficiency of the remaining existing nodes. So again, this diagram is probably going to be hard to parse in the minute I have to show it to you, but you can look at the paper in great detail, and you can build this diagram yourself by running the experiments in about 5 minutes, and I can show you exactly how this works in a minute. So what we did then, after we understood how to allocate to this topology, we looked at packet level simulations. So in this case, we did an all-to-all, the promised one, the global bandwidth benchmark, and we ran it on the 1,000 node topology here in this particular example. There is nothing surprising in this diagram. You see the non-blocking fat tree dominates everybody. Well, of course, it's 10 times more expensive or 15 times more expensive, so it better delivers full bandwidth. Otherwise, it would be a very bad investment. And many people build non-blocking fat trees. We can see that the other topologies are somewhere in the middle. The HX2 mesh is about 25%, and the HX4 mesh is about these 10%, 11% that I mentioned before. So nothing really surprising. The all-reduce results are more interesting because, as we mentioned, all-reduce is the kind of pattern that you can really map onto anything. Literally any topology will take your all-reduce, and especially those are quite nice. We have 2 different communication patterns, communication implementations for all-reduce. One is the ring implementation, which gives us optimal bandwidth, very popular in the machine learning area. And the second one is a torus implementation that uses 2 rings in 2 dimensions. And we can see the torus gets us half bandwidth, but on the left side, for smaller message sizes, up to, here in this case, 128 megabyte, we actually beat the ring implementation. But eventually, the ring implementation for 2 gigabyte and 512 megabyte will outdo all the others. But nothing super interesting here in the sense, because we just see that eventually we will achieve 100% of the bandwidth. Okay, so of course, micro benchmarks are getting you only that far. So I talked about all-to-all and all-reduce. 2 micro benchmarks, extremely important in deep learning, both of them. But what does that say about real application patterns in deep learning? Well, very little. These are micro benchmarks at the end. So what we also did in this paper, we actually implemented a set of what we call DNN communication proxies. So we implemented 8 applications in C and MPI code that represent the exact communication pattern and wait times for particular DNNs. So these 8 applications implement ResNets, BERT, CosmoFlow, DLRMs, GPT, various GPT versions, and mixture of experts. So these applications are actually of importance far beyond that paper, because other people are already using those to analyze completely different things, because these are communication benchmarks of real AI workloads. So they're quite nice. Again, they're also included on our reproducibility package, but I believe this benchmark is going to be far more important. So it's a portable C code and easy to adopt, so relatively simple to run, and again, you can reproduce all our stuff in this package. So I could now talk a long time about all of these results. So here's a whole list of them. Again, as I mentioned, ResNets, GPT, CosmoFlow, DLRMs for the HX2 mesh and the HX4 mesh. I just want to focus you on the right diagram, the HX4 mesh, which is giving us a little bit of an insight of the relative cost with respect to the Hamming mesh. So if it's bigger than 1, then we win. The Hamming mesh wins. And we can see here it's at least 1 on the right side in the HX4 mesh, but it's going up to 8.8x cost-wise for the ResNet case compared to some topology. So you can look all of these results in the paper yourself and interpret them how you want. But the last couple of minutes, I really want to use to talk a little bit about the artifact description appendix that we have in the paper. So as I mentioned, this paper was extremely challenging to run simulations of. So we actually really used these 0.6 million core hours on a supercomputer to run these simulations, because if you look at this table, just the all-to-all in the large case for the 16,000 processes consumed 21,000 core hours alone, just the all-to-all simulation. We have been pushing more than 120 billion packets through the network to make this happen. So this was a significant simulation effort. And now you may be wondering, oh gosh, how can I actually even work with this? Can I reproduce this? This is going to be hard. Well, hold on. My student, Tommaso, is a great person working in industry. He actually has an industry-grade, I would call it, reproducibility package that is already used by various vendors to evaluate topologies, which is quite cool. So we have a Docker image, which you can download in, well, depending on how fast your internet connection is, it's about 3 GB in size. But you can literally download the Docker image and run it, and you'll see it in a minute. But you can also download a compilation package of the SST simulator to compile it on your supercomputer. And I just had a conversation yesterday with Andrew Chen, who's in the audience, that there are multiple people in the community who use our reproducibility package to compile SST in parallel on a supercomputer, because it's not that easy. I mean, it took myself in the first time about 3 hours to get it going. Here you take about 10 minutes because we have it all scripted. So that's also an interesting insight. With that stuff, we basically have, for both of those, we have a common software stack that we have 10 Python scripts to run all the simulations, either on your laptop or on a supercomputer. We have more Python scripts to automatically parse the results and generate all the plots we have in the paper. Of course, now what you can do, it's the cool thing, you can change these a little bit, and you can basically create your own paper. I mean, the next step after this will be an interactive way where we can just run interactively and the plots will change as a Jupyter notebook. And we have a lot of documentation with an FAQ in the system itself or in the Docker image itself that I just want to give you a little bit of an insight. I would actually encourage you to download that container. I mean, you could do that right away. Well, as I mentioned, it's about 3 GB, so we are not waiting here. It's downloading quickly. Yeah, conference internet. So you can actually just load it into Docker. You can log into the image in Docker. You can just get the root in the Docker, and then you can explore the image yourself. So you can browse the container. You can look at it. It's really that straightforward. And you find various directories in there with lots of readmes. Then you can actually reproduce these benchmarks extremely easily. For example, a small topology random permutation benchmark, you just start the right Python scripts that are, of course, documented in the readmes how to do it. It'll run the simulation. Well, for that simulation, we would actually need to wait about 20 minutes on my laptop, so we just accelerate this. Then the simulation is done. And then you can just parse the results to other Python scripts. And you see here the median, high, low 1%, average times. And you can also get the plot immediately. So that was on the laptop. But 0.6 million core hours, you're going to wait until the end of time if you run this on your laptop. So you can do the same thing on the Pitstein supercomputer here. We're just showing that again. And we even have scripts for launching all these jobs through the Slurm batch scheduler. You can see it here if you're a supercomputing person, submitted batch job. And then all of these jobs do exactly the same thing as if they were running on your laptop and would create the same plots, the same output, and everything reproducible in this sense. Okay, so with that, I would like to conclude and summarize. So what did I say? Well, I mentioned that modern deep learning workloads are all about supercomputing. Right? So we are driving the future as a community. I'm very proud of this. First of all, second of all, the communication characteristics of deep learning workloads are quite limited in the sense that we can exploit them to build topologies. Co-design, like we've been dreaming of as a community for years, is finally happening. Then we co-designed that topology, the Hamming mesh topology, to get us really unprecedented cheap bandwidth, and we showed the practical usage of that topology. It's about 15 times cheaper for all reduce, 1.7 times cheaper for all-to-all than a fat tree, and it gets us significant speed-ups for real-world DNN proxies. Then on the reproducibility side, we have 8 DNN proxy applications that form a set of micro-benchmarks to run network tests against. And again, there are several companies that are already using those. They're quite happy that we did this. We spent 0.6 million core hours on 128 nodes. You can run this on your laptop if you're willing to wait a long time. But of course, the small topology, you can actually run in a couple of hours on your laptop, the 1,000 node. What I'm talking about here is the 16,000 node, which is going to take a year. And you can run it on a supercomputer. So, and we have the spreadsheet where you can do the topology configurator, where you can actually design your own cost-optimal topology for whatever purpose you want. So with that, I would like to thank you, and I'm open for questions.
Okay, thank you, Thorsten. So I'm going to ask you a question myself because I'm the chair.
Of course.
So in hyperparameter optimization community, they focus a lot on running multiple deep learning models just to optimize the architecture so that they can reduce the cost of training.
Yes.
What are your comments on this work and how it affects that community's work?
So if you do a massive hyperparameter tuning, you basically launch a whole set of different jobs that are not necessarily communicating. I mean, they're definitely not communicating. So in that sense, you don't really need network connectivity. But the nice thing about this topology is that, I mean, if you do the thing you just mentioned on a fat tree, you're going to waste a whole lot of money because you have an extremely expensive network sitting there not doing anything. If you do it on a Hamming mesh, that topology is extremely cheap. Right? So you're not wasting as much. So if you don't communicate, it's actually a good thing. So for hyperparameter tuning workloads, you're reducing your waste, I would say.
Okay, thank you. Further questions?
Thanks for the talk. So you mentioned that it took 21,248 node hours to model all-to-all large. How on earth it just takes 256 node hours to model GPT-3?
Oh, yeah. So GPT-3, we just run a single iteration of the thing because they're all the same iterations, right? So the first iteration is exactly the same as the last one. So GPT-3 is actually that run that we did is relatively small. It doesn't issue that many messages per iteration. The problem is to train it, you need a gazillion iterations to work with the thing. And the all-to-all is really bad because we had to run large messages. GPT-3 doesn't have that large messages. We ran hundreds of megabytes. If you've seen in the plot, it went to 2 gigabyte. If you send a 2 gigabyte message, you're going to send a couple of thousand packets. Each of those packets is going through every single switch, and that's the problem.
And what's the size of the system and what's the distribution? So was it fully pipeline and tensor and data parallel?
The GPT-3?
Yeah.
Yes. It was a three-dimensional. All of these proxies are three-dimensional parallelism, as I mentioned, and you can configure them. The exact details of which dimension was which size we have in the paper. I don't know off the top of my head. But yes, it implements all three: pipelining, operator, and data.
Thanks.
There's somebody right next to you.
I'm going to allow just one more question. Sorry.
Hello. Hi. You talked about reliability in terms of node failure, but in case of switch failure of the Hamming mesh part, how does it look that case?
So in case of switch failure, that's a very good point. In case of switch failure, you're basically blowing away a whole column.
Exactly.
And that column is then just gone. But our experience in practice is that switch failure is much less likely than node failures. So if you actually do the math, a switch has 64 ports. It's about 50 times more reliable based on lots of reliability data. So it's a wash at the end.
Yeah,
so
and
really
in terms of bandwidth, because across the Hamming mesh, because when you go to the switch, you will decrease 200 gigabit per second, 400 gigabit per second.
Oh, I love that question. Sorry, my answer may not have been clear. If a switch dies, we are not allocating anything to that full row or column.
No.
So the bandwidth is exactly the same. We just kill all of these accelerators.
That I agree. I mean, what is the bandwidth of the switch at the Hamming mesh? So you keep the same bandwidth within the torus inside,
Yes.
and also.
Everything is full bandwidth as soon as you leave your accelerator. So these are all 400G links in our simulation.
Okay, 400G links. So you're able to have 1 terabit per second always.
1.6 terabit per second.
1.
Yes. Yeah, we have.
Can you repeat, please?
1.6 terabit per second. Yeah.
Okay, perfect. Thank you.
Okay, thank you so much. Can we thank Thorsten again?